In the last two lectures, we've looked carefully at two important issues. One is the measurement of distance, and the other is the universe's expansion. Now, if you think about these two terms for a moment, you'll realize that our simple notions of distance need to be re-examined rather carefully. Here on Earth, for example, the distance between cities is fixed. New York to San Francisco is 2,600 miles apart, period. But what if, like the universe, the Earth were expanding? In that case, the distance between New York and San Francisco would be continually increasing. And the value of 2,600 miles is only true today. It was smaller in the past, and it'll be larger in the future. See, we face a similar situation with the expanding universe. When you want to discuss the distance to galaxies, you must recognize that this distance is increasing over time. And you always have to specify a time when you specify a distance. Actually, the situation is even trickier, because the universe can expand by large factors during light's journey from one galaxy to another. It's as if you set your car odometer to 0 when you leave New York, but while you are traveling to San Francisco, the Earth expands by 30%, say. So your odometer reading on arrival at San Francisco is neither the distance when you left, nor is it the distance when you arrive, but it's something in between. Now, in earlier lectures, I've glossed over these issues, and you may have already sensed something was confusingly missing. For example, in the astronomer's view of the universe from Lecture 2, you may have been puzzled why the Big Bang, which is supposed to be when everything is together, can somehow be far away at the edge of the visible universe. But this hides exactly the kind of ambiguity I'm talking about. In truth, 13.7 billion years ago, when the light set out, the material was very close to us. But today, when the light finally arrives, that material is way off, nearly 46 billion light years away. And the distance 13.7 billion light years, which I've previously used, in fact applies to the distance the light itself travelled. It's the car odometer's reading. It's neither the original very small distance, nor is it the present day very large distance, but it's something in between. So I want to spend this lecture clarifying these kinds of issues. And in particular, I want to look at how very remote things appear to us when we live in this expanding universe. And as we'll see, there are some really quite interesting and bizarre consequences. So let's begin by identifying three different distances using this diagram. At the bottom, at time t emit, light of wavelength lambda emit leaves a galaxy which is a distance d emit away, and it begins its long journey towards us. Now, as time passes, we move up the diagram. The universe expands, stretching both the photon's wavelength and the galaxy's distance. The photon arrives today, at time t now, when it has wavelength lambda now, and the galaxy is at a distance d now. Now, in the last lecture, we learned that the light waves and the separation of galaxies are stretched by the same factor. So we have the following simple relation. The ratio of d now to d emit is the same as the ratio of lambda now to lambda emit, which is the redshift stretch factor, or RSF for short. Now, just an aside here, astronomers usually use the symbol Z for redshift, which is RSF minus 1. But I'm going to use RSF in these lectures because it's a little bit more closely linked to the cosmic stretch. Okay, So we've now encountered two important distances, the emission distance and the current distance. What about the distance the light itself travelled during its journey? Let's call this the light travel distance, DLT. Back in our expanding Earth analogy, that's the odometer reading on the car driven between New York and San Francisco. Now, since light always moves through space at the speed of light, this is equivalent to always driving our car along the road at, say, 65 miles an hour. The light travel distance is therefore the speed of light times the journey's duration. So mathematically, we have DLT is c times t now minus t emit, where c is the speed of light, of course. But notice that the journey's duration is also the look-back time, how long ago the light was emitted from the galaxy. So we have the nice fact that the light travel distance in light years is simply the look-back time in years. This is the distance I've used previously when saying something like, that galaxy is 5 billion light years away, meaning we see it as it was 5 billion years ago. In fact, that galaxy was only 4 billion light years away when the light set out, and it's now 6 billion light years away today. Okay, now by far the easiest thing to measure for any galaxy is redshift. So a key question is, how do we use redshift to calculate our three distances? Now, the too quick answer is to say, use the Hubble law, with distance proportional to expansion speed. However, although that relation is true at any given time, as we look out, we look back to earlier times when the expansion speed was different. So the observed Hubble law begins to break down at large distances, and we need to modify it by folding in the universe's expansion history. Now, we've met the expansion history before. Here it is. The curve shows how the separation between any two galaxies grows over time, and it's scaled so that the separation today is labelled as 1.0. I've called this curve S of t, where S stands for size or scale or separation, and t, of course, is time. Now, I'm postponing to lectures 11 and 12 how to figure out the exact shape of this curve, but for now, let's just get the idea that the Big Bang occurs at time 0, when the separation of everything is also 0. The separation between objects then increases rapidly at first, but slowing down as time passes. Then there is a period of coasting, followed by acceleration as the effects of dark energy begin to be felt. So let's see how to use this curve to find our three distances. And to make things concrete, let's choose a galaxy whose redshift stretch factor, RSF, is 3. Now, if the redshift stretch factor is 3, then the universe must have been 3 times smaller when the light set out. So everything was a third as far away then. But that's just S of t, the scale factor or size factor for when the light set out. In fact, this is always true. For any redshift stretch factor, RSF, the scale factor, S of t, was just 1 over RSF when the light set out. So back to our plot of S of t, we simply find where S of t is a third, and we run across to find the time at which the light set out, 3.2 billion years after the Big Bang, or 10.5 billion years ago. So immediately, we have the look-back time. It's 10.5 billion years. And the light travel distance is 10.5 billion light years. So that's one of our distances measured. Now, getting the current distance, d now, is trickier. Here's how we do it. We start from the previous graph and focus attention on a small time interval during light's journey between t and t plus delta t. During that interval, the light moves a distance c times delta t, but that distance is going to get stretched between then and now. The amount it gets stretched is 1 over s of t. For example, if at that time the universe was half its current size, so s of t is 0.5, then our little length, c delta t, will expand by a factor of 2. That's just 1 over 0.5 by today. And this will contribute 2 times c delta t to today's distance. We can show this contribution by the area under a tall, skinny rectangle of height 2 and width c delta t. Now, to get the total current distance, d now, we must repeat this for all the little intervals between t emit and t now, and add them all together. But this is just the area under the curve given by 1 over s of t. Now, if you recall high school or college calculus, you'll recognise that the way to write this using a fancy integral sign, really, it's just this area. For our example galaxy, we get a current distance of 15 billion light years. Now, finally, getting the distance when the light was emitted 10.5 billion years ago is very easy. The redshift stretch factor is the same as the distance stretch factor. So the emission distance is just a third of the current distance. A third of 15 is 5 billion light years. So finally, a galaxy with redshift stretch factor of 3 has current, light travel, and emission distances of 15, 10.5, and 5 billion light years. We can use these area diagrams to show all 3 of these distances. Notice that, just as we expected, the current distance is always larger than the light travel distance, which in turn is always larger than the emission distance. Okay, having figured out these 3 distances for a redshift stretch factor of 3, how do they vary for the whole sweep of redshift, from very small redshift to very high redshift? Here you can see the rather fascinating answer. Nearby, all 3 distances are the same and are given nicely by the Hubble law. But at higher redshift, the simple Hubble law gets worse and worse, and the 3 distances become quite different. And amazingly, the emission distance actually becomes smaller at higher redshift. I know this sounds bizarre, but it makes sense when you think about it. We're looking so far back in time that the universe was so much smaller that the object was close by when the light set out. Now, here's an extreme example of that. This is our astronomer's universe. And remember, almost at the outer boundary sits the microwave background. And as we'll learn in lecture 13, the redshift stretch factor for the microwave background is 1,000. And doing the calculations, we find that the look-back time is 13.7 billion years, almost back to the Big Bang. And the current distance is a huge 46 billion light years, but the emission distance is 1,000 times smaller than this, which is only 46 million light years. So bizarrely, the microwave background is extremely distant, but it was relatively nearby when the light set out. Now, with this background in place, let's consider how very distant galaxies appear to us. There are some really very interesting effects. So first of all, the rate at which processes seem to unfold within galaxies slows down. Now, this has nothing to do with Einstein's famous theory of relativity, but it happens simply because light paths get stretched by cosmic expansion. For example, if a supernova goes off in a distant galaxy and lasts, say, a week, then the light waves leaving that galaxy span a distance of 1 light week. But when they arrive at our galaxy, that wave train has been stretched longer, so it takes longer to fully arrive, and so the supernova's duration seems longer to us. Actually, here's some real data showing exactly that. At higher redshifts, going to the right, the duration of the supernova appears to get longer by an amount equal to the redshift stretch factor. Now, what about a distant galaxy's brightness? Obviously, we expect more distant galaxies to appear fainter, but by how much? Remember from Lecture 6 that a galaxy's brightness normally follows the inverse square law, so B equals L over 4 pi d squared. Remember, L is the luminosity of the galaxy and d is its distance. But in cosmology, which distance do we use? In fact, we use the current distance, d now, because when the photons arrive, they're spread over a huge sphere of radius d now, an area 4 pi d now squared. Of course, the current distance is the largest of our 3 distances, and so for this reason alone, high redshift galaxies are very faint. But the situation is unfortunately even worse than this, because 2 other effects make the galaxies even fainter. First of all, redshift reduces each photon's energy, so we collect wimpier photons. And then second, the time slowing effect that I just talked about reduces the rate at which the photons arrive. So the final formula for brightness is B equals L over 4 pi d now squared times 1 over the redshift stretch factor squared. So at high redshift, this second term is important and galaxies appear much fainter than you would expect. Well, now let's consider how big galaxies appear to be. Normally, when somebody walks away from you, they appear smaller and smaller as they get further away. Remember from Lecture 6, the formula that gives the angular size of an object in degrees is 57.3 times the size of the object divided by its distance. So just as before, which of our 3 distances do we use? The answer is that we use the emission distance, because the photons' directions are set when they leave the galaxy, and they remain unchanged from then on. Now, this is actually great news, because remember, the emission distance stays relatively small, even at high redshift, leading to the bizarre fact that galaxies at high redshift do not appear to get smaller. In fact, at very high redshift, they can actually appear bigger because they were closer when their light set out. This graph shows the size of a typical galaxy at greater and greater redshifts. After an initial drop in size, they settle down to about 1 to 2 arc seconds across. Difficult to observe, but not impossible, especially from space. This magnifying effect of cosmic expansion is really a wonderful gift from nature. Now, unfortunately, nature still doesn't make it easy for us. Almost as important as size is a property called surface brightness. How bright is a galaxy per unit area on the sky? And it's simply the ratio of the galaxy's brightness divided by its angular area. Now, normally, surface brightness doesn't in fact depend on distance. Basically, push an object further away, and of course its brightness drops at the same rate as its angular area. So the ratio stays the same. But in our expanding universe, the situation is much worse. The brightness drops even faster, and the angular area gets larger. So their ratio, the surface brightness, takes a nosedive by the fourth power of the redshift stretch factor. So for example, a distant galaxy with a redshift stretch factor of 5 has a surface brightness that is 600 times lower than a nearby galaxy. Now you can see why it's so difficult to study high redshift galaxies. They are desperately faint. Their angular size is a very tiny 1 arc second, and their starlight is redshifted out of the optical band into the infrared. It's for these reasons, of course, that cosmologists eagerly await the successor to the Hubble Space Telescope. It's called the James Webb Space Telescope, JWST, named after the man who was primarily responsible back in the 1960s for ensuring that scientific research became one of NASA's primary goals. It's a large, infrared-optimized space telescope with a 6.5-meter mirror. As we'll see in Lecture 19, it's only with telescopes like this that it's possible to study the remote and therefore young universe. Now, at this point, I'd like to introduce a type of diagram that can sometimes really help us grasp the odd effects of living in an expanding universe. And it's called a space-time diagram. And I want to introduce it in 2 stages. First for a static space, and then for an expanding space. So this figure shows a simple space-time diagram with the x-axis for distance measured in light years and the y-axis for time measured in years. If we are stationary, our x position is fixed, and it traces out a straight vertical line, like this. Here's a planet, fixed 10 light years away, and also it has a straight line, like us. Now here's an alien spaceship, which leaves the planet and travels to the Earth. Now perhaps the aliens send a light signal rather than a spaceship. How does light move on this kind of diagram? Here it is, travelling from the planet to us. Notice how it moves at a 45-degree angle, since for every year of time, it gets 1 light year closer. Well, so far so good. Now let's consider an expanding space like the universe. So here's a similar space-time diagram with a vertical line for our galaxy, while here's a line of another galaxy, which is currently 10 billion light years away, moving with cosmic expansion. Notice that its path looks just like our earlier plots of the scale factor, S of t, but it's rotated so that time now goes upwards instead of to the right. Here are the paths of 2 other galaxies. They're just copies of the first galaxy, one nearer and one further. Now you can really sense the expansion. All galaxies have paths starting at the origin, which is, of course, the Big Bang, and at any later time, the speed at which they move away from us is just proportional to their distance from us. That's the Hubble law. Now, here's the tricky part. Let's imagine we observe a distant supernova in this galaxy. What path does the light take? Here it is. When the light sets out, moving at light speed, it travels through a space which is itself moving. So the light makes slower headway than in a static space, so the initial trajectory is steeper than 45 degrees. But as the light gets closer, where the expansion is slower, it makes faster progress, finally arriving at a 45-degree angle, since the local space is, from our perspective, essentially static. Finding our 3 distances for this supernova is very easy. Here's the current distance, here's the emission distance, and here's the light travel distance. Easy. Now let's push this out to the limit and trace the path for light coming from the Big Bang itself. Its shape is fascinating, so let's take a look at that for the moment. So shortly after the Big Bang, cosmic expansion was so rapid that light was caught like a swimmer in a fast current. It was actually dragged away from us by the expanding space. For over 3 billion years, the light receded from us, ultimately being dragged nearly 5.5 billion light years away. Only later, as the light made its way into slower moving space, could it begin to close the gap. And then ultimately, after a 13.7 billion year journey, it enters our local, almost static space and streaks into our telescopes at light speed. Now, this curved path has a very special status for us here on Earth at the present time. And for reasons I don't have time for, it's called our past light cone. On it lies everything we currently witness in the universe. Notice how each galaxy's path crosses our light cone at a particular time. That is the time we witness when we see the galaxy in our telescopes today. 7 billion years ago, for example, the photons from this supernova joined many others on our light cone, all heading towards us and destined to arrive at Earth today. Now notice that our light cone, what we witness, is only an infinitesimal fraction of all that there is. It's a line within a plane. There are many events in the universe. These are places on the plane with a specific time and distance, which are not on this line. This is pretty obvious when you think about it. The light from ancient events occurring nearby obviously arrived long ago, while the light from recent events occurring very far away will arrive in the far future. So each time has its light cone, and together they cover the space-time plane. But at any given time, today for example, we only see what's on one light cone and everything else goes unseen. Okay, let's finally use this space-time diagram to identify the furthest things that we can see, what one might call our visibility horizon. Basically, how big is our visible universe? It's defined, of course, by how far light can travel since the Big Bang, for which the look-back time is 13.7 billion years, the full cosmic age. So we want to go back to the full 13.7 billion years of look-back time to find that galaxy's trajectory, which just touches our light cone at the Big Bang. Here it is, and it's further than any of the other galaxies that cross our light cone at more recent times. Here are our three distances. The look-back distance, or time, is 13.7 billion years, and the emission distance, d-emit, is of course 0. That region was on top of us when the light set out. This makes sense. 13.7 billion years ago was the Big Bang, when everything was together. But the current distance is 46 billion light years away. So that matter which we see out at our visible horizon, roughly speaking the microwave background, has by today condensed into galaxies just like ours, and they're currently sitting 46 billion light years away. That is our visible universe. Anything further? And we've not yet seen it. Well, this has been a challenging lecture, so let me briefly review the main points. First, we recognize that the concept of distance is tricky in a large, expanding universe. For any observed galaxy, there are three important distances: the emission distance when the light set out, the current distance when the light arrives, and the distance the light itself travelled. We looked at how to calculate all three of these using the measured redshift, and a knowledge of the universe's expansion history, S of t. A rather interesting feature is that the emission distance actually gets smaller for galaxies at high redshift, because they were closer when their light set out very long ago. Overall, we found that when we observe very distant galaxies, their time seems to slow down, they appear to get bigger, and they get very faint. We then recast a number of these themes using a space-time diagram. This nicely shows the cosmic expansion starting at the Big Bang. It also allows us to plot how light moves across the universe. Light coming from the most distant regions started out being carried away from us by the rapid early expansion. But ultimately, it made headway and finally manages to arrive. We also use this diagram to find the size of the visible universe. We see the Big Bang itself at the maximum look-back time of 13.7 billion years. It was right here when the light set out, but ultimately it spawned galaxies that are currently 46 billion light-years away. It's a visibility horizon, beyond which we cannot see. But just like we know there are lands beyond our terrestrial horizon, so in later lectures we'll learn there are galaxies upon galaxies stretching well beyond our cosmic visibility horizon.